Hi. In this video, I'm going to introduce you another model that involving first order differential equation, which is decay model. Or we said, usually the most famous one that you study in chemistry and physics, it will be called the radioactive decay model. Usually we were using radioactive as a model to explain the decay model. Alright. For example, you know that there is a radioactive substance, right? Radioactive substance, which is initially the difference between the proton and the neutron. Alright, it's very radioactive because of the mass of the atom is very big, right? It's very big. For example, radium or plutonium, those radioactive substance which have a bigger mass of the nucleus, right? Usually they will be decay more, right? They will decay more. Maybe they have many radioactive ray come out from the mass release. So which is more energy release when they exposed to air, right? Because they're very explosive. Because why? Because it's very radioactive. Okay, the decay is very fast. Okay, the rate of decay very fast. So it means that after some time, maybe for many years, it will still, let's say for 1 million years, it will be still radioactive. But the rate of decay may be slightly lower than this, because the isotope for this one become more stable, right? As you learn, so become more stable, which the mass of the object become lesser, right? Become lesser, and after for some time and getting year by years, maybe for 1 trillion years, for very long, okay, the mass become more stable. Means that the rate of decay become lesser, and maybe one day it becomes stable, a stable atom, right? So what I'm trying to explain here is the decay constant. Okay, I can relate this by using the m. Alright, the mass means that the mass of the isotope, alright, of the radioactive substance here. So the dm dt is also directly proportional to the mass of the radioactive substance. Because why? The bigger the mass, the higher the rate of decay, right? You see, the smaller the mass, the less decay, right? Because initially they are unstable, right? They are unstable. The mass of the nucleus means it's very big, right? So they are very according to chemistry and physics, it's very unstable. So they release a lot of alpha, beta, gamma particles in order to make it stabilize the isotope, right? So that's why when the mass is bigger, the rate of decay also bigger. Alright, we used to explain this way. So from time to time, it's reduced. So it means that the bigger the mass, the rate of decay. But because of this model, it's actually a decay model. Decay means the mass of the substance is actually decreasing, right? Compared to the growth model, population growth model. Population growth model, the number of the number of bacteria is increasing, right? But this is decreasing, right? Even though it's directly proportional, but in nature, it's actually decreasing in mass. So usually we will put a negative K here to denote. Okay, without the negative is okay, right? But the negative is just to denote that this is actually a more decreasing model. Means that it will be dm dt equals to negative K m. This is our model for decay. Decay. For anything that decaying, for example, a body of a organism that already die, so it will be decay also from time to time, right? So it can be represent many things as long as decay. This is the model, right? A simple decay model. So we can rewrite this by finding the formula for the mass of the substance. So by dm dt, we can write this to be dm over m equals to negative k dt. This is start with apply the concept of differential equation. Means you have to know some science, right? You have the knowledge of science, then you have to know how to derive the formula to describe. You have to use the mathematical language to describe the process of the decay, right? This is the greatness of mathematics and science. So dm over m is negative kt. So now I have to integrate both sides, right? So 1 over m, we have ln m. And this we have negative kt plus c, right? So as we integrate, the k is a constant, so integrate dt, so we have to integrate 1, we have t, right? So we just add a constant here. So we derive the formula as this will become negative kt plus c, exponent, right? So it's a log base e, right? The e can go in there. So, and we rewrite this to be e negative kt multiplied with e to the power of c. Multiply is because of the plus here, right? It is turned to be multiply. So, and this is also a constant. We will let this to be a. So this is the decay model. The decay model for this problem here. Means that a radioactive substance or something that are decaying can be using this formula. This formula comes from this differential equation by using the concept of separable variables. Okay, this is a simple models. Okay, as you're sketching this type of graph, as you see before during your physics class, okay, physical science class, you will look this type of graph which you have seen before when you study about radioactive substance, where you have half-life, all right? You have half-life. Actually, I tell you, this is actually the there is an initial mass here. So there is an initial mass here, and when t0, when the time is 0, there is a mass. But after some time, the mass turns to be half of the initial mass. This is called the half-life, right? And this curve, the radioactive decay curve, is actually the reaction curve is actually according to this formula. And the constant of A and the constant of K is depend on the types of radioactive substance. It can be radium, they have different K, plutonium have different K, or any radioactive substance, they have different type of decay constant. This is called the decay constant. We set this to be a decay constant. So they have different graph, right? They have different graph. So this, but all the graph will have this formula, just different of A and K. This is an exponential graph, right? So, okay, let's look at the examples. All right, let's look at this example. I just want to tell you that how the first order differential equation apply for a decay model. For example, these cases here. So this is a case where there is a 10 gram of plutonium, right? Everyone know that plutonium isotope is a very radioactive substance. It's categorized as a highly radioactive substance. So, which is 10 grams of plutonium, just 10 grams. Was released in a nuclear accident, right? How long would it take for the 10 gram to decay to 1 gram? Means that we want to know 10 gram to reduce to 1 gram take how long, right? So if it take very long, means that it's a very severe accident. Means that it's take times, or it's very dangerous. To want to see the dangerous of this substance here, right? So let's see. We have to calculate, right? As a scientist, we have to calculate how long will it take for the 10 gram to 1 gram, right? So now we have know that from the derivation just now, we have known that the mass of the radioactive substance is always directly proportional to the mass of the substance, right? It is always true for any radioactive substance or anything that are decay. So, and we have dm over m and km, right? As we put k, so as we integrate both sides, you have to derive the formula, right, to explain the process. So finally, you have getting m equals to ae negative, sorry, there is a negative here, negative kt, right? So this is a decay model. So as you know, you have to derive to tell them what is going on for this substance here, to represent this is a decay constant, which is I have derived in the early of this video. So you have to rewrite this to explain this model here. So now our purpose in this question here is not, I'm not going to derive this for you. I just want to tell you that how to apply this model in solving this problem. So we have to find the value of K and value of A, right? K and A. So then we look at this question here. Was released in an accident. How long will it take for 10 gram to decay to 1 gram, right? So means that initially we have initially we have T0 and the gram, right? So means that the mass will be 10 gram, right? And we actually know that the half-life, right? We actually know that the half-life of this plutonium, which is given in the question, is actually given the half-life, right? Given the half-life of plutonium. Half-life of plutonium is actually T equals to 24,100 years. Wow, right? It's very long. 24,100. So means that this is the half-life. So what is half-life? Given that the half-life of the plutonium isotope is 24,100, means that the mass of the object means that for the initially the mass is m, for example, is m. When t is 0, the m is m naught. So when after 5 years, means that after, for example, we have 10 gram here, right? We have 10 gram here. So means that the initial mass here is actually 10 gram, right? 10 gram. So means that for the mass to become half, right? This is called half-life. Means that from 10 gram become 5 gram, it will take about 24,100 years. Wow. Right? This is the information given. So it means that once they give you the half-life, you know, if at the first, when the accident happened, the initial mass means that will it take for the 10 grams, right? 10 grams. So means 10 grams at the start is T0. So means half-life. Half-life means half-life for plutonium means after 24,100 years, the mass of the 10 gram will only become 5 grams, right? Half of the mass, but take very long, right? So now what they want is, what is the mass of the plutonium after what is the time taken, right? What is the time taken for the mass of the plutonium become 1 gram? Can you imagine how long is it, right? For 10 become 5, it become 24,100. So from 5 become 1, it will take how long? So we cannot just give a number. We have to calculate, right? We have to calculate. So let's calculate. So we have to use this first two information here in calculating the constant for A and E for these cases here. All right. Okay. Let's start with the first. So initially there is only 10 gram accident release, right? So now we check, okay, M is 10, the mass is 10, okay, A is a constant, we don't know, right? E, negative K, the time is 0, so we substitute T with 0, so it will become E to the power of 0, right? E power of 0. So then we have A equals to 10, right? A equals to 10. So we have M to be, we have improved the formula by the constant A we know is 10 E negative KT, right? But we still lack of one information, the K, right? So how to find the value of K? So we have to substitute, we have to use this information, the half-life, to find the value of K. Let's see. Right? Okay, let's find the value of K by using this information here. So I have teach you the techniques. So as M is become 5, right? 5 equates to 10 exponent negative k is take 24,100 years, right? The time. So it means that 5 over 10 will become half. This is half-life, 24,100 k, right? So then you have to find the decay constant. So by putting ln both sides, we have ln 1 over 2, ln 1 over 2, which is, if you put ln e, right, it will become 1, and this you bring over become 24,100 k, right? So if you're solving this, you are getting k to be negative 1 over with 24,100 ln 1 over 2, right? You can always change this become a decimal value, but I will always retain the value to make sure the values of the finding will be accurate, right? I always prefer exact value, all right? So let's see, now I have a constant and I have the value of A. So now I have a complete formula for this plutonium, all right? This is for plutonium. So it means that, all right, so the formula will be, okay, I just write here. So if M equals to the 10, right? The 10 exponential negative kt, right? Negative k, which is become positive 1 over 24,100 ln 1 over 2. This constant, this is the decay constant, all right? This is a decay constant. So it's a decay constant multiplied with T. And I tell you that this is the formula for the plutonium with initial mass of 10 gram. All right. So means that this is the formula for this incident here. All right. So now, very simple. What is actually they want? They're asking how long would it take for the 10 gram to become 1 gram, right? So your purpose here is to find the time taken for it to become 1 gram. So I have to substitute the M with 1 gram. All right, let's substitute M with 1 gram. So 1 equals to 10. So you will get the value of 1 over 2,400 ln 1 over 2 T, right? So as you substitute, you're getting 0.1 and exponential of 1, and you're putting ln both sides, all right? You're putting ln both sides, 1 over 0.1, you're putting ln both sides, you're getting 1 over 2,400 ln half T, right? And eventually you will find the value of T, which will give you approximately 80,059 years. All right, this is show that how dangerous is this substance, right? It's taking 80,059 from 10 gram to 1 gram. All right, this is the dangerous of radioactive substance. All right, that's all for this video.